As you start into Chapter 9, we're going to be covering an Algebra 2x topic of roots, powers, and logarithms. And the first section is 9.1, and what we do is we address 5 different objectives. If you take a note here, these 5, the first one you are going to evaluate nth roots in exponential and radical form without a calculator, and then also with a calculator. Number 3, you're going to graph and determine the domain and range of nth root functions. Having finished your project, it's going to be very similar to that, but more in the real graph format. Number 4, apply nth root properties to area, volume, and rate problems. So basically just doing some word problems with nth roots. And number 5, determine the number of real nth roots of a particular number. So I just want to jump right into the notes and let's go ahead and do that. Now the first 2 objectives talked about nth roots in both exponential and radical format, and that's what you see right here. This is considered the radical format. This is the exponential format of an nth root. Another word for it is a radical. And let's talk about this. I want to look right at the mental math component where it says evaluate exactly over the complex numbers. When they say over the complex numbers, just means you can have imaginary solutions. If we look at letter A, the square root of 36 means what number 2 times is 36? Hopefully you realize that that number is 6. They ask you for part B, what is the square root of negative 25? So that question is what number 2 times gives you a negative 25. Hopefully you can remember when we did the imaginary numbers, this would actually be 5i. 5i times 5i is 25i squared. I squared is negative 1. So the square root of negative 25 is 5i. Okay. Then we get into a different one. We get the cube root. If they want to know the cube root of 27 means what number 3 times gives you 27. It has to be the exact same number, and the answer here is a 3. And then part D is the cube root of negative 8. The question is what number 3 times gives you a negative 8? And if you think about it, that number that's going to work is a negative 2 3 times. Therefore, the answer to this is negative 2. So this is just a review of how you look at nth roots in the radical format. Now, we looked at what the radical format looks like. We can also look at the exponential format. And here's what the theorem says, is when x in here, in this particular format, when x is greater than 0 and n is an integer, then x to the 1/nth is the nth root of x. And all this means is this. What is 125 to the 1/3 power? What you can do is you can rewrite that as a radical. This is the cube root of 125, which means what we did on the previous slide, what number 3 times gives you 125. The number that works would be a 5. So 125 to the 1/3 power is the number 5, and that can be done without a calculator. Part B, 1/2 power, is the same as saying the square root of 1 over 36. We just don't write the squared in there. It's implied that it's there, but if you want to write it there, you could. Again, we just typically don't. You can break a radical up by doing the square root of 1 over the square root of 36. Square root of 1 is 1. Square root of 36 is 6. Therefore, 1 over 36 to the 1/2 power is the same as saying 1/6. Now, part C, this third one here, they want us to find negative 16 to the 1/4 power. Be very careful with this one. This negative has nothing to do with the 1/4 power. If they had written this problem like this, then this would have mean the 4th root of negative 16. Because it's written in this case, that negative is just sitting out there, so it's negative on the outside, and then it is the 4th root of 16. So what it asks you is what number 4 times is 16. The answer to that is a 2. So the 4th root of 16 is a 2. That negative sitting on the outside, so the answer is negative 2 for this particular problem. Again, do be cautious though. If it had been this problem we would have the fourth root of negative 16, and there is no real answer to the fourth root of negative 16. It's actually impossible to do. Now, this next slide just addresses our objective number 2 of evaluating this with a calculator. Not hard to do. To put this in the calculator, you're just going to do 6 to the caret. Be careful. It's to the whole exponent of 1 over 50. And when you do that, you're going to end up getting to the nearest millionth. Do the correct position on that. You're going to get 1.0364885. This is the tenths, hundredths, thousandths, 10,000ths, 100,000ths, and millionth position. So just be careful in finding the millionth position with the calculator. Now, part B of this, they want the negative of that. Again, be careful. This here is raised to the 50th, or 1 over the 50th. So it's really negative on the outside. And as a radical, if you wanted to write it, it's the 50th root of 6. You would just punch that in your calculator as this. You would do negative. And you would get the same answer, but as a negative answer from the one above. Now, as we move on, this next slide applies the third objective, which says graph and determine the domain and range of nth root functions. This is an example of an nth root function. And if you graph this, the parent function, depending on what n is, we want to define it. For example, if n is 2, this would be x to the 1/2 power. Okay. If we make n is 3 or n is 4, what's going to happen, for example, if n is 3, that's going to tuck in a little more. This is x to the 1/3 power. If you do n is 4, that one is going to become x to the 1/4 power. So you could just try that in your calculator and notice by changing the exponent there is going to cause that curvature. The domain and range of this is pretty straightforward. The domain is the x's, so we have x activity. It does start at 0 and it goes everything this way. So the domain typically are x's greater than or equal to 0. The range of this function, the height starts at 0 and goes all the way up. So the range is typically y is greater than or equal to 0 also. Just look specifically on the graph. If it's translated or slid someplace else on the graph, the number may not be 0 in this particular case. Now the fourth objective wants you to apply nth root properties to area, volume, and rate problems. And the next few problems are actually going to do that. Here's our first example of an application of it. A bowling game cost 50 cents in 1960, and it might cost $3 in 2010. What is the annual growth rate? When they taught growth rate, they're talking an exponential growth. Remember, exponential growth from first semester can be written as y equals a times b to the x power. B here is what we call the growth or decay factor. Okay. This can also be broken down into just a little more detail. We can do y equals a. And the factor can be written in terms of 1 plus or minus r. That's what b can be. And this right here is the rate. So the 1 plus or minus r we call the growth or decay factor. The r itself is the growth or decay rate. Now they're telling us what's the growth rate. So if we set this up, remember a is our starting amount and y is our ending amount. So we start this problem, our initial cost is 50 cents. The final cost of the game in 2010 is $3. I do not know the b, the growth factor on that, but I know from 1960 to 2010, we've had 50 years go by. So we have 50 years right there. Now to solve this, we would just solve an exponential equation. To get b by itself, we have to do two things. We must get rid of the 50 cents in the 50th power. First thing you want to do is divide both sides by 0.5. When you do that, you're going to get 6 is equal to b to the 50th power. To get rid of that exponent of 50, multiply by its reciprocal of 1 over 50th. So b is going to be equal to 6 to the 1/50th power. You put that in your calculator. you're going to get b is approximately 1.036. This is the growth factor. The growth rate is embedded in there. The rate is right there. So the growth rate, you could say, is 0.036. Written as a percent, you would move it 2 back. It's a 3.6% growth. So this is an annual growth. And we would say that the cost of a bowling game would grow annually at 3.6% every year from 1960 to 2010. And that's how you do a rate problem. Let's go ahead and look at a volume and area problem on the next slide. All right, in this case, it has the volume of a cone with radius r and height equal to the radius is given by the formula. Volume equals 1/3 pi r cubed. They want us for part A to give the formula for the radius in terms of v. So what they want is they want the radius here in terms of v. So what we need to do is solve the equation for its radius. So let's just take this equation and solve it for the radius, and we'll see what should go here. So if we take that, volume equals 1/3 pi r cubed. To get r by itself, we need to get rid of the 1/3 and the pi both. I'm just going to look at it like this, you guys. I'm going to say volume equals pi over 3, by the way, in r cubed. That's fine. To get rid of a fraction, the easiest way is to multiply by its reciprocal. So let's just do 3 over pi over here. So we're going to have 3v over pi is equal to r cubed. To get rid of the cubed, you can multiply it by the 1/3 power, or you can do the cubed root. So if we do this whole side here to the 1/3 power, we could have this, that the radius is equal to either 3v pi to the 1/3. If you wanted as a radical instead of an exponent, you would say the cubed root like this, 3v over pi. Those are equivalent and mean the same thing. So that is part A. Part B, a cone with a radius of r and height equal to its radius. It has the volume of 60 millimeter cubes. Use the formula of part A to find its height. So what we want to do here, the height and the radius are the same thing, so it's already set up. All you need to do is put the volume in here. So put 60 in for the volume, and you're going to say r is equal to, we'll just do 3 times 60 over pi. Get that answer and raise it to the 1/3 power. When you do that, we're going to get approximately 3.86 millimeters is going to be the height of this particular cone. And that is covering objective number 4. Now in this slide, we are going to address the 5th objective, is determine the number of real nth roots of a number. And they're going to break it down into even and odd functions. And the first one is this. They're going to say, what if we have an nth power that's odd? So what you might be used to seeing would be something like this, like y equals x cubed, y equals x to the 5th, and so forth. And if you have an odd function that's as basic as this, what you're going to see is it's going to look something like of this nature. And you're going to see that it has rotational symmetry at the origin. Remember that from the first semester we learned functions that rotate at the origin are odd functions. And you're going to realize this. There's exactly one real root, no matter the degree of the function. In Chapter 7, remember when we learned if something was the 5th degree, there's up to 5 zeros for this function, or 5 roots. How many of them are real? They could be made up of real and imaginary. They're saying here, if we have an odd function, there's going to be one real root. And let me show you how to use this. Let's have, in this case, n be 5 for the equation, and we'll have the y be negative 243. So if you put that into this equation format, it's going to look like this. Negative 243 is equal to x to the 5th power. To solve this, you would raise both sides to the 1/5 power. So you're going to have negative 243 to the 1/5 equals x. What number 5 times gives you negative 243? That's actually going to be a negative 3. And what this is saying is if you were to take this particular equation here, and if you graph that, you're going to end up seeing that this graph will cross the x-axis at -3. You're going to see one real solution. You know, something of this nature is what you're going to end up getting. And that's going to be the case whenever you have an odd function. It will guarantee to cross the x-axis one time and have one real root. Now, for an even function, what they're saying here is if the exponent here is even, so like y equals x squared we're used to seeing, or y equals x to the fourth, the power is even, so it's called an even function in this case. And typically, some functions that look like this will have reflective symmetry in the y-axis, and that's what an even function looks like. It has to have reflective symmetry in the y-axis. So in this case, it works very much like a parabola, even though if it might be x to the fourth or x to the sixth. It can have three different types of real solutions. It can have 2, 1, or no real solution. And let me show you an example. If I had something like this where it was written as 81 equals x to the nth power, and it was a fourth root, for example, if I said let n be 4, because n is even for that one, and I wanted to solve it, what I would do to solve this is I would say 81 is equal x to some fourth power. What number is that? Well, to solve this, you would take the fourth root. So what is the fourth root of 81? So you're saying 81 to the 1/4 power. And what number 4 times is 81? Well, you would have either a +3 for this case or a -3. And so you actually have two solutions. Now, if you were to take this and graph this equation, you'd see that it actually crosses the x-axis at 2 spots, at +3 and -3. Okay. Now, another example is what if we had not 81, but it was 0, and you had 0 equals x to the 4th power. And to solve this, you'd say 0 to the 1/4 power. What number 4 times is 0? The only number 4 times that 0 is 0 itself. So there's one real solution. Well, if you graph this function, what you're going to find is this function actually crosses at, in this case, the origin. It touches the origin. There's one real solution, and that's it. Now, the third case is if there's no real solution, and that problem might look something like this. What if they had -81 here is equal to x to the n, to the 4th power, I'm sorry again. And to solve for x, you're going to take the 4th root of -81. What number 4 times is -81? There is no such real number, so there's no real number. No real. And if you graph that, what you're going to see is something on the graph is this. It's never going to cross the x-axis, so you're not going to see the real solution. So this here is really just a review of what we've learned in the past. Now here's what I want you to think about. How many real 50th roots does the number 6 have? So what that's saying is this. 6 is equal to some number to the 50th power. What number would that be? You know, as you think about it, you could solve for x, by the way. X would be equal to 6 to the 1/50th power, and you'd get your calculator out. And you're going to get one answer on your calculator. But what you need to realize is this number right here, the 50th power. In this case, their n is 50. Well, n is an even number. If n is an even number, it has 2 real solutions. So what's going to happen is when you put this in your calculator is going to give you an answer for this. It's going to give you one of them. You have to realize that it's plus or minus in this case. So that's where the plus or minus comes from. Now, if the exponent here was not 50 but 49, for example, we know that there would have to be one real root because it's an odd power. So you can tell if there has to be one real root or 2 real roots from that one. And sometimes if you have an even power, by the way, keep in mind when we just talked about you could have 0 real solutions, or you could just have 1 if the vertex sits on the x-axis. Now this next slide we've actually already talked about it, and what it addresses this, let me just summarize it super quickly. When we had an even function, right, when we said we had an even function, we talked about the fact that we could have two real roots. It could cross the x-axis twice. We also could have 0 real roots where it never crosses the x-axis. There also could be 1 if it's even, where it sits on the x-axis. We've addressed that. We also said when it's odd, that an odd function we know has to cross at least one time. So what this is doing is just saying, hey, can you give me some tricks to remember? Really, it's more for the even function. If you look at what I circled in the red, the even functions are the ones that could have 2 roots, 1 root, or 0 real roots. The odds are always going to have 1. So let's just clarify real quickly the difference. The one that's going to have the even, will have 2 real roots is this. 81 is equal, x again to the 4th power. They're saying for every positive real, if this is a positive number, you're going to have 2 answers. And in this case, it was -3 or +3. Okay. Another example, they're saying, what if the number is negative? Fine. If the number was negative for the even case, we might have this. We might have -81, again, to the x to the 4th. What number is going to give you 4 times a -81? They're saying there's 0. In this case, there's 0 roots. And then the last one you might have, again, what we already looked at, is they're saying if the number is 0, 0 to the x to the 4th power, if you solve that, you're going to end up getting that there's 1 real root. So they're just giving you some tricks to look at what the number is for that. Or just think through it, and it should be helpful. So come away from this. If it's an odd function, an odd power, it has 1 real root. If it's even, it's 2, it's 1, or it's 0. You just have to think about it logically in terms of what it would be. Now, I just want to show you this. We've already talked about it a little bit. Radical notation we've addressed. Example number 4, they want the square root of -64. Another way to write that as a radical, or that is the radical as the exponent, is -64 to the 1/2 power. It means what number 2 times gives you -64. If you put that in your calculator, it's going to say no real solution. Let me tell you this. Go to your calculator and hit the mode button. There is a mode button that's going to be very helpful. Instead of having your mode be real, you can change your mode on the bottom part to a plus bi. And if you go and change it to a plus bi, and then go out and now type in your calculator the square root of -64, it's actually going to give you the imaginary number of 8i. Okay, so again, change your mode to this. And you can always be in a plus bi mode. That's actually the safest mode to be in. The real mode will just error out. If it's imaginary, it's going to say that there is an error. Now to confirm it, how can you confirm it? All you have to do is realize 8i times 8i. So do 8i times 8i, and that's going to be 64i squared. I squared is -1, so it's -64. Because by definition, square root means what number 2 times gives you the -64? An 8i and an 8i, and this is all you have to do for the confirmation of that. The very last slide I want you to look at is just notice the difference between these 5 examples. Examine the following in which are real numbers. I want you to take a minute, pause the video, and just tell me which of these 5 will give you actually real number answers. Pause the video. When you pop it back up, I'm going to show you all the answers to this, and we'll talk about which ones are real numbers. If your calculator is in the a plus bi mode, what you're going to see is that the first 2, a and b, are the same answer, just written as a radical versus an exponent. Part C is just the negative on the outside. Part D and E is a negative of the number. The 4th root, so what number 4 times gives you -33 for these 2 here? It's never going to happen in the real world. They're imaginary numbers, so that's why you'll get the imaginary complex format here. For the homework assignment, modified is going to be based on your Chapter 7 test performance. So go back and look and see if you got an A- on that or not. But you can go ahead and skip numbers 10 and 20 for the regular assignment, and for the modified, skip number 20. Let me know if you have any questions. The answers are posted on the Google site. Good luck on the homework.